you have it, or?
Problem 24.
Okay, what's
For the
24?
theoretical.
Okay, well, I'll do this one, and then I'll do my spiel. All right, unless you have another one. Okay, now problem 24. I don't remember what that is.
Do I have an alternative expression for the compression factor for the van der Waals equation?
Oh, wow, that one's hard. Okay, so alternative expression for the van der Waals. Okay, now I just want to point out that this is a pure algebra. We're not really doing much calc in our, and when we do calc, remember that our calc really is first semester, like first month of freshman calc. Most of what you're doing is algebra. And on the exams, I have calc identity. So you're never really doing calc. Okay, when we did compression factor, which, God, I believe that's the compression factor, is that right? Yeah. And so I ended up just multiplying this. Yeah, so this ended up being, what I did in class was this. I mean, it's just childishly simple, right? So then I end up with A, RT, VM, RT. Yeah, is this right? So you can see that this is clearly close to 1, and then this will simply shave off. Sorry, that's a greater than 1, and then this is less than 1. So there you go. Now, what happened was when I was writing a test question, I was going to do it based on this, but I suddenly started doing the derivation differently. I did the algebra differently, and I came up with a different expression. And I thought it was kind of fascinating that I did that. And the expression I came up with was, remind me what the question says, because I don't quite recall how to find that. I think I multiply. Well, let's see. Now I can figure it out because it looks like I multiply by VM minus B and divide by RT. What does it say?
It's multiplied by VM minus B.
It says to do that, right?
It just tells you to prove the expression that you wrote.
Wait, does it tell you how to start?
It says to multiply.
By VM minus B.
Right. So I can tell that what I was trying to do was turn it into an expression of 1 plus or minus something plus or minus something. So what that does is it makes it more clear what drives you up and down. That's why I like that question. That's why I put it on the homework. Okay, now the way to do this, and again, this is just algebra practice, but the problem is with these types of questions that if you start out on the wrong step, if you start out doing it the wrong way, you'll never find it. You can, but it can be 20 steps as opposed to 2. And when that happens on the exam, stop. If you've done 3 or 4 steps and you have not hit the answer, absolutely stop what you are doing. I have seen so many people do 20 steps and not get to the answer. Listen to me right now. None of the questions are answered in 20 steps. If that happens, stop. Even if you're done except for this question, check the other questions. You are subconsciously answering the question. You just don't know it because that's subconscious. Come back to it in like 5 minutes. You have 2 hours for the exam. You can do that. Okay, now, in my advanced algebra think, or more accurately, I actually wrote the question, I can see that I can find the 1 right here by multiplying everything by VM minus B, and here's what I didn't put in there was to divide by RT. So, VM minus B over RT is equal to 1 minus A times VM minus B over RT VM squared. A minus B divided by RT. Someone starts screaming at me if I do this wrong. So I got PVM minus PB. Looks like lead. PB. Okay, there's my compression factor. 1 minus A RTVM plus AB over RT VM squared. Okay, so
We're just left together in the solution.
wait, what?
In the solution, you just left the term as A times VM minus B over RT.
Okay. I see. Yeah, I see what you said here. Let me get lost in my own little thinking here. Um, um, Yeah, I know I gave you the answer, and what you're saying is I left it, I didn't factor it, I just factored it here, and that's just because I felt like it. I'm sorry, my handwriting's a little rough. Other than the factoring, is that right? Okay, okay, yeah, so there you go. Now what I can see is the B term drives me up off of increases compression factors, and A drives me down. It's the same thing I had uncovered last time. It's just a little bit more clear. Perfect gas and then deviations from the perfect gas. It's just a little bit more clear. This is a term I probably would cancel. A and B are very small, and so I bet that those don't really contribute too much. So anyway, so I mean, there you go, I've done the question. Most importantly, what I've told you is a test taking strategy for these. This is exactly what I would do on a test. Maybe actually a little harder than I would hit on the first test, what I would go for on the first test, just because it's got a lot of stuff. Don't be afraid of all the letters, they're just constants, right? Just don't forget them. Other than that, yeah, there you go. Question?
I think I missed it, but why did you press that last time?
I guess I didn't on the answer key. I'm just saying, if I was to do further derivations, and we actually are, that's one reason that this thing is on here, we're actually going to do something with this in chapter 5, this expression. I'm just saying that in terms of what matters, perfect gas, up, down, this is going to be small. This is going to be small because A is small, B is small, and A times B is very small. So, again, I remember too much. Because we're going to use this to understand refrigeration, that term gets wiped out. I'm actually kind of getting you ready for that when we do it about a month, 2 months from now. Any other questions? We're okay? Yeah, all righty. Okay, so last one I want to go over is I just wanted to do some practice with partials and remind you of some things here. Actually, maybe, I think I have enough time.
I actually have another question for the homework.
Okay, another question? Which one? Because maybe I can do it quick.
18.
What's 18?
It says the van der Waals equation of state predicts the residual volume of a real gas is the limit of Vm minus Vm naught equals V minus A over RT. If this gas is actually a perfect gas, can you tell me what is the value of A that makes this true?
Okay, now this is an example. I'm not going to. All right, so I just spilled my guts and gave you one of them. So I'll give you a hint on this instead of answering it outright. Residual volume. I was kind of rushing yesterday when I was doing the residual volume, but residual volume of a perfect gas. What do you think it would be?
0.
Okay. Now, given that expression, what is it? B minus A over RT, right? What makes that 0? And I asked you for you to solve what A, right? What value of A makes B minus A over RT equal to 0?
BRT.
Huh?
BRT.
Yeah, sure. Yeah, A is equal to B over RT. And then I just gave you the answer. And then part B, you actually plug in numbers, right, for helium and nitrogen. And then you'll see how much that's true. In nitrogen, it'll be like, they won't be perfect, but it'll be close. And helium is going to be, the residual volume is quite high. And that's because it has compression factors for Z are greater than 1. Z is an oddball. Z has compression factors that are, the pressure of helium is always higher than it should be. That's what a compression factor means. That's what it means for a compression factor to be greater than 1. Yeah? So I spilled my guts and answered the question. Yeah, so we're okay? Any other? Okay, so I want to, again, I never cancel class because you paid me, and that's absolutely absurd. I'm just not going to do it. Again, I'm not going to go about the thing. But now here's the thing. I didn't get a chance to point this out because I'm really bad at time management. Remember how I had this? I want to tell you a little bit about exact and inexact equations. And then, anyway, so this is kind of cool. Okay, so I said that this is an exact thing, but what I didn't get a chance to mention was it means something more than being path independent. Again, we had a little chart of a little thing hopping from point to point, and I showed you that which path we took didn't matter. But here's another cool fact about exact versus inexact. Now, remember that this is the change of an f, and f is clearly a multivariable thing because there's x's and y's. Give me a function that the derivative or partial derivative is this.
Or
X times y. X times y. Sorry, my handwriting's off today. X times y. That's right, x times y. F is x times y, and now this is also terribly important. Remember that the way we define a partial is that we let one variable change while the other's held constant, and then vice versa. And again, this is terribly, terribly important. This is the starting point of all our thermodynamic proofs. df dx, when f is xy, is y. And the change in f with respect to y, when f is xy, is x. And I don't know why I wrote equal. There we go. Okay, so there you go. Okay, well, so what? All right. What did I do? What did I do for the other one? I said x dy, or was it y dx? I think it did x dy. What did I do? I just did half of it. I did y dx? Okay, I did y dx. Okay. Oh, you're going to love this. What's the function? Seriously, what is it? If you could answer this question, what is the function, the derivative of which is that? If you could answer that, you'd win a Nobel Prize. Does not exist. Isn't that nutty? Seriously. When I read this for the first time, I was like, no, I can figure this out. It's x over y. And then apply this formula, you'll always end up with two terms. See, that's the magic, is that I got rid of one of the terms. I swear to God, there is nothing you can come up with that's going to do this. So the function doesn't exist. Now remember the first day I said it's not clear that energy exists, only changes of energy? This is one of the reasons. Right, if F was work, and Y was minus exterior pressure, and X was volume, there you go. It's the same thing as work, force times distance. But so therefore, what does work equal to? Don't know. No one can derive a formula for work. There isn't one. There's only a change of work. It's kind of neat. So sometimes some textbooks, especially if you do Pekin for biochemists, they don't want to overwhelm people, so sometimes they'll just write W, but you can't. It always has to be, a partial, little d or a big D, right? A little d or a big D. So there you go. It's kind of a neat thing. And even for a couple of hours, I tried to come up with something that would do that, and you can't. It just doesn't exist. Apparently supercomputers are working on this, and they can't figure it out. Okay, now with that, I'm going to actually try to trick you into thinking that what I just said isn't true. I'm going to give you an example. Now, here's another thing. Here's another thing about this. Okay, so work I can't write, before I just start doing a math problem, that's actually all I've got. Before I go further, I will never present for you a formula for work. Only a change in work, and then there it is, I'm done. We'll do some other types of work at the end of class. We're going to do surfaces, because that's important for nanotechnology. That way we're not teaching things always from 1800. But I can never write down work. I can also not do this for heat. Heat is also inexact, but it's a little harder to understand, so we'll wait till chapter 4. But remember, I just wrote internal energy was work and heat. I said that at the beginning of the last lecture, and this is exact. So whenever I present a thermodynamic thing that is exact, I always will show you what the function is. U is not hard. We're going to cover that next time. What's real interesting is entropy. I'm going to show you what a change in entropy is, but I should be able to write down what is entropy. I'll give you here's an example. What about Gibbs energy? Maybe don't even write this down, but you know that Gibbs energy is H minus TS, right? So there's an example. Hell, I'll give you one more. Enthalpy. Now, don't worry about this. We're going to cover this. is u plus PV. So you've probably seen some of these before. You've definitely seen G is H minus TS. But again, what I'm going to do with all these energies, I'm always going to give you the change, and because they're exact, I will then transform them into functional forms, but I cannot do that for work and heat because it doesn't exist. Anyway, so that's kind of the dealio with exact and inexact partials. Okay, now with that, I still got plenty of time. What I'm going to do is I'm going to give you an example that does not seem that way at all. And let me, yeah, I'll do that. And then I have a couple more kind of other examples to show off if you feel like. Let's see, what do I want to do? Let's see here. Let's say, okay. Here's one other thing I want to start getting across because I'm going to do a lot of this. Let's do df dx. And let's say it's equal to x. Now, one of the things I've alluded to, and we're going to see a gazillion times more of this really, really soon, is that I can manipulate partials like a juggler manipulates kittens when they juggle kittens, which happens. It's horrible, but it happens. The f is f, change in f is x dx. Okay, so you've seen what I've done is I've just multiplied each side by the partial of x. Again, you can do that. You can juggle them algebraically, and then you can do things like integrate them. Okay, the change in f is, and therefore f is 1/2 x squared. Okay, there you go. Okay, do you see what I just did? Before I integrated that, isn't that inexact? Something d something? Isn't that inexact? But I just found the function. The thing I told you I couldn't do. Your resolve? Your partial was the partial of the existing variable. Yeah, it's not the same. It has the same form, but it's not exactly right. It's not y dx. It's x dx. Those are not the same. So I can integrate it, and this is the correct functional form. So anyway, that's just kind of a neat thing, a neat trick. But I want to give you, in the same vein, I want to give you an example that makes exact, inexact a little bit more clear. It's this kind of clever, it's like a math puzzle. And it hopefully, this is like the archetype example of exact, inexact. I think I got this off Wikipedia, by the way. But let's do, okay, so exact versus inexact. Let's talk about a person that goes from point A to point B, and it's in the x direction. And I'm going to define an exact partial and an inexact partial, and they're going to correspond to things that are real, and again, that's what we do. And one of them is net distance. Okay, and what's happening is a walker, a person, oh no, let's make it a kitty. Hello, kitty. And she's barfing all over my bed. Damn cat. What do you got? Grew up everywhere. So, kitty's going to walk from A to B and then from B back to A. And I'm going to define two partials and integrate them. One will be exact and one will be inexact. This one, I believe this is the one that is exact. Okay. The change in net distance is exact. Okay. And, okay, so what is that? Let's go from A to B. And then, you see I drew that curve, so we're going to come back. Kitty's going to come back. So what we're going to do is going from A to B, let's integrate that. Let's see, we're going to go, we're going to end up at point B. We're going to start out in point A. And let's call the net, let's call it, symbology, I'll call it the change in n. And given that it's along the x-coordinates, I can then give you a form for the change in n is just the change in x. And then this ends up being b minus a. Okay, and this, by the way, if you're like, what the heck did I do? It'll be a little bit more, I just changed an n to an x. That's literally all I did, but you'll understand why I did that in a second. Now, let's do b to a. So we're going to end up at a. So Kitty turned around. Kitty turned around. We're doing net distance. And of course, it should be 0. Kitty didn't ultimately go anywhere. Aliens who looked down at the cat at the beginning and at the end saw the cat in the same place, said there was no difference, and that would be what an exact function should do. Anyway, yeah, this is quite trivial. A minus b. And then, right, this plus this is 0. So the cat did not travel anywhere. All right, so again, that's an exact partial. This is kind of stupid and it has cats in it. So let me do something, this is like way more fun. Let's do total distance. So let me get rid of this, because again, this is like childish. Let me do total distance. This gets a little bit more interesting, a little bit more college level. And it shows off a inexact. Total difference is inexact. The change in total distance. And I will use the symbology dt. Now, before, I had an n turn into an x. I can't do that in this one. That's why I was doing that silly trivial thing. Okay, let's do the first leg. What we're going to do is integrate from b to a dt. And this will be the change in total distance on the first leg. Now, here's where it gets different. Now, before when I was doing net distance, I just turned the t into an x. That's all I did. It was stupid. Okay, but now this is different. What happens is the direction matters, right? There has to be a path dependence to this. Direction matters. So what I have to do is use what's called a sine function. The sine of the change in x times the change in x. Okay. So what? Okay, what the sine function does is sine of whatever. Here, I'm going to graph it. In a plane +1 -1. Okay, I know I'm in the way. So dx is negative, dx is positive. The sine is -1, so this is the sine function. It's -1 if the partial of x is negative. The sine function is +1 if the change in x is positive. It's a little phenomenological thing. All right, so this ends up being, if you do this, what do you get? You just end up with BA. The sine function is positive, so it ends up just being B minus A. Okay, now let's do the second leg. Where we're going to A to B, oh yeah, initially at B, we end up at A, dt. Now the sine function is negative. And so that's going to be minus A plus B. And so the net is 2B minus A. There you go. Yeah, I remember. Total distance. Total distance is, it matters that the cat went all the way to B and then back to A. Notice that then, if B is like across the room or across the country, like that was that movie Homeward Bound with the dog that finds its family, which I think they make that stuff up. There's no way an animal crosses the country and smells there. That's ridiculous. Anyway, they made that up for publicity. But anyway, so you see the point is it matters. It matters what the path is. If B is very far away, then the total distance can be very different. Whereas the net distance, if the animal returns to its starting point, is always the same no matter how far it went. One's path dependent, one's not. So now, again, that's kind of obvious. Now here's where I want to inject some college level stuff. is this not the function? I told you that I cannot write a function, the derivative of which is inexact. It is impossible, yet I seem to have done that. Again, I'm trying to trick you again into thinking it's possible. Because this is the thing, right, so here it is, that's the function. It's being integrated. Okay, here's what the thing is. It's actually not true. So let's think about what does this. If I can integrate this, then I've beaten this whole exact, inexact thing. So I'm gonna wipe this out here. And now remember, this sine function is basically what gets integrated. That's basically the function. So if I can integrate it, then I've got the function, the change of which is an inexact partial, which I'm saying you can't actually do. Now the problem with that, in this example, is I'm pretty sure I can't integrate this. What I could do is, it looks to me like the integral of this is the derivative of this. Okay, let's see. The derivative of this is -1, and then the derivative of this is +1. Looks like I did it. So this function, the derivative of this function, looks like this. And this function, of course, would be an absolute value. So it looks like I've just I just got you. Now you may be thinking, oh, but absolute value doesn't have itself a functional form. Actually, it does. It's the square root of the square. Absolute value is the square root of the square. So there you go. And that's a very high school calc, freshman calc function. This is definitely something I can work with. So it looks like, again, I have beaten this whole inexact. Looks like I've written a function. If I take a derivative, looks like my inexact partial. The thing I'm not supposed to be able to do. However, there's a trick. Let's see. Okay, now again, the derivative of the thing. So let's take the derivative of this thing. And hopefully you recall how to do this. So you take the exponent down, and then you take the derivative of the inside. Okay, and so this ends up being, whoa, what am I am at -1/2. That's the derivative of the inside function, right? 1/2 down, 1/2 -1 is -1/2. Okay, the 2's cancel. X over the square root of x squared, which is actually x over the absolute value of x. Okay. Which -1/1 looks like that. It looks okay, except at x equals 0. Technically, it's undefined. So this is kind of cheap. I almost feel bad about this. I almost feel kind of wasted your time. I have a couple more examples if you feel like. You almost have it. This is the only example where you can almost integrate an inexact partial and get a function. You can almost do it. In this case only, but it's not defined at 0. 0 over 0. In fact, technically, I think it's infinity, but anyway, that's something apparently mathematicians debate. So again, just another example of an inexact differential that has no functional form. No matter how tricky you get, it can't be done. And again, this is going to come up a lot in class. So with that, I have a couple more. That's really all I've got on that. I got a couple more examples of things I could show you if you feel like, or if any of you have a homework question. I've got one more important thing that I might should talk about. But how about I do that and then giving you time to think? It looks like we might end early because I've only got one more thing to talk about that could be like slightly important. And then after that, I really don't have anything and probably should just break and beat the cold home, right? When it comes to I won't call it F, I'll call it Z. or not? Is something exact or not? Now, the rigmarole I just went through was quite painful. And it turns out that Euler, E-U-L-E-R, Euler, it's Euler. You look like a fool if you don't say it right. Euler came up with a way to figure this out just by looking at the thing, looking at the partial and figuring out whether there was a function behind it or not. And it turns out, I thought this was kind of fascinating. Now, z will be a function of x and y. So now, of course, when taking the derivative with respect to y, x better be held constant. And I think I showed you this before. When it comes to double derivatives, you've got to do this funkiness when it comes to holding one or the other partial. Okay, what Euler said is that if the change in whatever is exact, then this would happen. You could permute the order of differentiation and get the same result. It only happens if there's an actual function behind it. Only then would this work. Now, I'm going to show example. This guy ends up becoming central to about half of our thermodynamic proofs. So this is one thing you want to know. I actually meant to bring it up in class because I promised you I wouldn't bring up things in class. And I just actually ran out of time, so I'm going to reiterate it on Monday. But again, if something is exact, if there's a function behind it, then if you take the derivative with respect to y or x, it's the same as if you took the derivative with x, y. The order doesn't matter. Only if there's a real function behind it. Unfortunately, we're not really ready to do these types of proofs yet. But why don't I, just for the heck of it, just to get you a little bit more okay with your math stuff in case you've gotten a little bit rusty, and we'll break a little early. I mentioned to you, I had some examples that are relevant. We're not going to do anything quite this hard, not that this is hard in this class, but you're going to do it in 346. So I wanted to show you some examples there. And again, this is just a little bit of math practice. So also to remind you of, I just want to make sure that you've got some math practice. Derivatives of exponentials, God, you're going to do a zillion of them. 346 is all about derivatives and integrals of exponentials. More integrals, actually, so you better be able to do the differentials. And, okay, with respect to y, actually just brings down an x. And then when I have the derivative of x, and I've got two x's, then unfortunately I've got to use a product rule. So I take the derivative of the first one and leave the second guy alone, and then vice versa. I've got an x, but then I'm going to bring down a y. Okay, so there you go. Now again, this has to be exact because I've written down a function. So this better be the same freaking thing. It has to be because I've written the function already. So there's no way that this isn't going to work. Okay, dx. And again, if I remember my formulas for derivatives of e to the whatever. Okay, I've got that. And no, sorry, I keep. And then let's see. Okay, product rule. And then all that happens is that my x and y get permuted here, but that doesn't matter when it comes to multiplication. So there you go. So showing off it's exact.